Okay, electron configurations of ions. We looked at this a smidge. So anions form when atoms gain electrons. And so then what we're doing is we're adding electrons to the electron configuration. That's not too hard. Cations form when the atom loses electrons, so we have to subtract electrons from the electron configuration of the atom. So when you're removing electrons, we have to know which electrons to remove. For the main group elements, we just remove them in the reverse order of how we would have put them in. So for aluminum, here's the electron configuration for aluminum, and it goes in this order: 1s, 2s, 2p, 3s, 3p. So when we take them off in reverse order. We take this one off first, and then we take these two off, and we end up with this electron configuration. Okay? This electron configuration is the same as that for neon. That's why aluminum forms a +3 ion, because it's stable in that way. That's the main group. Main group elements are the ones that are more predictable than the transition elements. So here's the transition metals. So for transition metals, you always remove the valence electrons first, even if that's not reverse order of filling. So if we look at iron, so here's the electron configuration for iron: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So the valence electrons are these guys, these guys right here, right? Highest level, biggest big number, okay? Don't worry about the little numbers. It's the biggest big number, any of them in there, add those together, there you go. So we have 2 valence electrons. Those are the ones that are going to come off first. You take those off, and now we're getting this electron configuration, because we just took those guys off. That's not reverse order of filling. So there's the iron 2 ion. There's also an iron 3 ion. After we've taken the valence electrons off, then you peel them off in reverse order, and so we'll take off one of these 3d electrons. And so this is what we end up with for the electron configuration for the iron 3 ion. For the iron 2 ion, it would look like this. Any questions? So in iron 3's electron configuration, the orbital diagram shows us that there are 5 electrons that are not paired. 5 lucky electrons get to sleep in their own bed in the hotel, right? Well, the number or the existence of unpaired electrons has to do with whether an element is magnetic or not, attracted to a magnetic field. So a substance is paramagnetic if it has unpaired electrons. It will be attracted to a magnetic field. And that's because those unpaired electrons generate their own little magnetic field because they're spinning. A charged body that's spinning causes an a magnetic field. A diamagnetic atom or ion has all of the electrons paired, and that's going to be slightly repelled by a magnetic field. So anybody have a stainless steel refrigerator at home? Do magnets stick to it? Nope. But if you have an old-fashioned one, magnets stick great, and you can cover the whole thing with leftover menus and stuff, right? I don't know if that's good or bad, but why are some metals magnetic and some are not? Aluminum can. Magnet won't stick to this, right? Iron faucet, it'll stick just fine. Has to do with whether there are paired electrons or not, unpaired electrons. It's only going to be the valence electrons that could possibly be unpaired, because it's going to fill up until you get to the valence shell, and that's the only place you're going to see unpaired electrons. So we have to somehow remember that paramagnetic has unpaired, and diamagnetic, they're all paired up, right? So I'm not even going to tell you not to think about the thing that messes me up, because then you'll think about it. So diamagnetic. What does the prefix di mean? 2. So diamagnetic, all the what's that word? Electrons. All the electrons come in pairs, kind of like Noah's Ark. Okay. Diamagnetic, they're all in 2s. Okay. Paramagnetic, they're not all in 2s. Some of them are singles. Okay. It's the best I've got. Write the electron configuration and orbital diagram for each ion. Predict whether each will be paramagnetic or diamagnetic. Okay, so we got cobalt-2 ion. So cobalt comes after argon. So here's argon. And then what's the rest of the electron configuration? 4s2. Let's do cobalt, not the ion first, the atom.
3d7.
3d7. Okay. Because with transition metals, you need to be careful when you write the ion. If you don't think about it, you'd write 4s2 3d5, and that's not going to be right. Because what comes off first for transition metals? Valence electrons. So it's these guys that go away when it forms a +2 ion. So here's the electron configuration. Argon 3d7. Let's look at the orbital diagram. So there's 4s, no electrons in that one. Having troubles. This is not my best work. So putting these guys in, stick them in their own beds first, right side up. Okay, there's 5. And now the next 2 have to pair up. This is the 3D sublevel. Are there unpaired electrons?
Yes.
Yes. Okay. So, paramagnetic or diamagnetic?
Paramagnetic.
Paramagnetic. They're not coming in 2s, diamagnetic. These guys are not coming in 2s. So this is paramagnetic. So let's look at the nitride ion. So that's going to be helium. And again, let's look at the atom first. So helium, 2s2, 2p3. Yeah, sorry, brain fart. Having a very gassy day with my brain. Okay, so there's nitrogen. The 3- charge means we've got 3 extra electrons. So it's not just 3 here, there's 6. Okay? So the orbital diagram, we've got 2s, and we've got 2p. And we've got 2 electrons in there, and 6 electrons in the 2p. Any unpaired electrons? No? They're all coming in 2s. So it's what? Diamagnetic. The nitride ion is not going to be attracted by a magnetic field. The cobalt 2+ ion will be. Any questions? Yes? It is 6 instead of 3 because this has a 3- charge on it. And it gets that charge by adding 3 electrons. When you're doing ions, I think it's always best to do the atom first and then figure out, am I adding or subtracting electrons?
So on the first one, you took off the 4s2 because there was already some before that?
I took the 4s2 off because the 2+ means it's lost 2 electrons.
Oh.
And it's a transition metal, and so instead of taking off from the 3D, we take the valence electrons off first. Any other questions? So we talked about atomic radius. What about ionic radius? Cations are a lot smaller than the neutral atom. What happens when you make a cation is you're taking valence electrons off. and you're generally taking all of them off. So you're basically peeling a layer off of the atom, which would make it smaller, right? On top of that, the effective nuclear charge is increasing because you got rid of the existing valence electrons, but now you have new valence electrons that used to be core electrons. So the number of core electrons has gone down, so the effective nuclear charge goes up, and that's why we see these huge changes. So from lithium to lithium plus, losing one electron, we go from a radius of 152 picometers to 60 picometers. It's less than half as big. And it's mostly due to increased effective nuclear charge. And that trend always works. The cation is always smaller than the neutral atom. Any questions? Anions are larger than the neutral atom. And thankfully that makes sense as well. You imagine taking this atom and slapping some extra electrons on it. What's your gut feeling about that? If you put extra stuff on something, is it going to get bigger or smaller? It's going to get bigger, and it does. So, like oxygen here, oxygen atom is 73 picometers in radius. The oxide ion, 2 extra electrons, it's almost doubled in size, 140. You're adding electrons with no change in the nucleus. And it's not obvious from the little simple calculation we did, but this does result in a lower effective nuclear charge. Because there is some shielding between valence electrons. We just kind of glossed over that. But an anion is going to be larger than its neutral atom. Isoelectronic. Iso is a prefix that means the same. Electronic refers to electrons, right? So isoelectronic ions are ions that have the same number of electrons. And that's kind of meaningless if you talk about ions of the same element. So we're really talking about ions of different elements. So sulfide, chloride, potassium, and calcium ions all have the same number of electrons. Sulfur has gained 2 electrons, and so it has 6 protons, but it's got 18 electrons. Chloride has gained 1 electron, 17 protons in the nucleus, 18 electrons because of that added electron. Potassium's lost an electron, calcium's lost 2 electrons. They all have the same number of electrons. The numbers of protons are different, though. So calcium has a higher effective nuclear charge. It also just has a higher charge period on the nucleus. It's got 20 protons as opposed to sulfide only having 16 protons. And so we see that sulfide is larger than calcium, and there's this trend because the effective nuclear charge is increasing as we go from sulfide to chloride to potassium to calcium. Increasing nuclear charge pulls the electrons in tighter, makes the thing smaller. Any questions? So, predicting ion size. Choose the larger atom or ion from each pair. So, potassium or potassium ion, which is bigger? Potassium. So, I explained it in kind of a more thorough way, but the simple way is think about, well, what's the difference between these? How do I make a potassium ion from a potassium atom? I take an electron away. Well, you know, if you're wearing 15 coats and you take one off, are you going to get bigger or smaller? Smaller. Maybe not much, but you're going to get smaller. So, well, this one must be bigger then. Fluorine or fluoride? Fluoride. Because here you're putting another coat on, right? You're getting bigger. That explanation does not account for the huge size changes we see, but it'll get you through problems like this. That's good enough. Calcium or chloride? Let's get a look at it. Okay, this one requires more thinking.
Are they the same?
No, they're not the same. So why aren't they the same? Well, first of all, let's see, how many electrons do they have?
Calcium is 20, but it's plus 2, that means that's 18.
Yeah, so calcium has 20 electrons. I'm sorry, it's got 20 protons. 20 protons. It had 20 electrons as a neutral atom, but it's lost 2 to become this ion, so it's got 18 electrons. What about chlorine? How many protons? 17 protons. Originally had 17 electrons. Minus 1 charge means it's also got 18 electrons. So these are isoelectronic. There's no differences in the electrons, so then we have to look at the difference in the nucleus. This one has a higher charge than that one. Higher charge is going to pull them in. So you could think of higher charge as being stronger. I sometimes think of the nucleus as being mom and the electrons are the children. If mom is stronger, she can pull those kids in more than if mom's weak and then they're just kind of all over the place. So the larger will be which one? Chloride. So easy to get it backwards. Okay. Questions? Ionization energy. Well, atoms don't just like lose electrons. They're not just walking along and an electron falls off. Right? The electrons are held there by a variety of factors, but you can make an ion. It requires energy, though, to pull electrons off of an atom. So ionization energy, or IE, is the energy needed to remove an electron. And we define that as from the atom or the ion in the gas state. The ionization energy is always going to be positive. I think of this as I'm going up to this atom and I'm like, hey, I want your electron. And he's like, well, you got to pay me for it, right? So I have to give him money. I have to give him energy for him to give me the electron. For the atom, that's positive. He got money coming in, energy coming in. So ionization energy is always positive. You always have to pay to pull these electrons off. IE1 is the first ionization energy, the energy to take the first electron off. So there's some metal element, atom here in the gas state, pay him some money, some energy, and you get the ion, and here's the loose electron that you can go off with. The second ionization energy is, okay, this guy's already lost 1 electron, and now we've got to give him some more money and pull a second electron off. And then there's the third, and the fourth, and the fifth, and you could just go down the line and pull off all the electrons one by one. Any questions? There's trends in ionization energy. So what we see is the first ionization energy decreases as we're going down a group. So helium, neon, argon, krypton, xenon. As you go down the group, it's easier and easier to get the electron off. Why? You're pulling off a valence electron. As you go down a group, the atoms get bigger and bigger, and the electrons then are farther from the nucleus. The attraction is proportional to 1 over the radius. The farther you are from the center, the easier it is to pull off. Okay, and so here's one of my just not politically correct sorts of analogies. Think of a large family and a small family. Okay, so I've got 6 kids, so I'll be in the large family group, and then I have a friend who only has 1 child. That's the small family. So in a large family, just kind of necessarily, your kids are going to be more spread out. I mean, you only have 2 hands, and there's 6 of them, and you can't hold on to all of them, right? So they're spread out. This is why we don't go to the fair. 1 child, mom can hold on to that child. Keep the child close. So ionization energy, kidnapping the first child. Okay? Who's easier to kidnap a child from? Big family or small family? Big family. Like, I can't even keep my eyes on all of them at one time, right? I'm happy when I know that they're all in the same state. But it's harder from the small one. So that's a non-scientific explanation. It's a lot harder to pull an electron off of helium than it is off of neon. The electron you're pulling off of xenon, I said neon, off of xenon is farther away. It's easier to snatch. Now we see that the first ionization generally increases across a period. So this trend is exactly opposite of the radius trend, right? And that's how I tend to remember it. If the electrons are closer, it's harder to pull them off. They're closer in a small atom. So as you go across, like from lithium to neon, we see that the ionization energy in general, there's some glitches, in general it increases. Because the effective nuclear charge is increasing and the size of the atom is decreasing. Any questions?
Is that what tends to make the larger atoms less stable? The larger elements less stable?
That it does have an effect on larger elements being less stable because they ionize more easily. Yeah.
They leave electrons at the particle numbers.
Yeah. Yep. So here are some numbers. We see as you go down any of these groups, there's a nice trend of the ionization energy decreasing. It's a lot easier to pull an electron off of a bismuth atom than it is off of a nitrogen atom. They're just farther away. As we go across, there's this general trend of it increasing, but there are some glitches. You see this glitch here. Beryllium has a higher ionization energy than boron, and nitrogen is higher than oxygen. There's actually a reason for that, and quantum mechanics explains it. But let's just look at these periodic trends. Which has the higher first ionization energy? So tin or iodine? No. Yes, sorry.
I was like, what?
I hadn't thought it through yet. Okay, so as we're going across, this is how I remember it. I have to think it through. Going across, they get smaller. Smaller means harder to pull it off. So higher first energy for iodine. Calcium or strontium? There's no gap in between there. Calcium. So as we go down, the atoms get bigger, right? Bigger atom, easier to take off. So we're looking for higher ionization energy is the calcium. So easy to screw these up. Okay.
It's one of those.
Yeah.
If possible.
Yeah, carbon and phosphorus is one of those. So there's carbon, here's phosphorus. Going across, we would predict that phosphorus is harder because it's smaller. But if we look at the trend going down, that says that phosphorus is larger than carbon, and carbon would have the larger ionization energy. So, not possible.
But if you had to choose.
If I had to choose, I would probably choose carbon.
Carbon?
No.
Phosphorus.
Phosphorus. Yeah, I would have to choose phosphorus. Fluorine or sulfur? So here's fluorine, here's sulfur. Now this is a diagonal, but it's not conflicting trends. Going across predicts that fluorine is smaller, so we'd say, well, fluorine has the greater ionization energy. The trend of going down says that fluorine is smaller and fluorine will have the higher ionization energy. So here the trends reinforce each other. Fluorine's got the higher ionization energy. Exceptions.
Of course.
Of course, you've got to have exceptions. So I pointed these out. So boron and beryllium, there's a glitch there in the trend. So let's look at the orbital diagrams for boron and beryllium. So for boron, so we've got 2s and 2p. How many valence electrons does boron have? 3. So 1, 2, 3. And then beryllium, how many valence electrons? 2. So they're in here. So when I ionize beryllium, I'm pulling that one off. Excuse me. And when I'm ionizing boron, I'm pulling this one off. What's different about those? This is in the 2s sublevel. This is in the 2p sublevel. Which of those sublevels has higher energy? The 2p. Higher energy sublevel is less stable, easier to take off. This is easier to remove than this one because the 2p sublevel has a higher energy. It's less stable. The other differences between these are very, very small. And so it's that difference in the sublevel energies that causes the glitch. I'm not going to make you remember the glitch, but quantum mechanics explains the glitch. Questions? We have another exception between group 5A and 6A, like between nitrogen and oxygen. So nitrogen and oxygen. Let's identify which one are we pulling off. So for nitrogen, we're going to pull off this one. And for oxygen, we're going to pull off that one. So here we have this nice half-filled sublevel. And here we have a half-filled sublevel plus one guy, plus one electron. This electron, because it had to pair, is easier to pull out of there than one of these electrons. These guys are pretty happy. Hey, we've each got our own beds. This is cool. Here, this one is having to share with that guy. Successive ionization energies. So looking at how much energy to take the first one off, how much energy to take the second one off. So it's a little about, I talked about buying electrons off of this atom. So I pulled one off, I paid him for it, and then I'm like, okay, I want to buy another electron. He's like, well, I already got rid of one, now I kind of need these, and so I'm going to have to pay him more than I did the first one. So for sodium, the first electron comes off, it requires 496 kilojoules for a mole. The second one, 4,560 kilojoules. It's huge. What happened here is for sodium, when I took the first one off, that was that valence electron. So that one came off kind of easy, but what do I lose after that? Core electrons. If we look at sodium, 1s2, 2s2, 2p6, 3s1. So the first ionization energy is pulling this guy off. Okay? After that one's gone, now I'm into what were the core electrons. These are closer to the nucleus and they're going to be harder to pull off. So there's a leap between taking off the last valence electron and taking off the first core electron. For magnesium, that happens after the second electron because magnesium has 2 valence electrons. So the first one's 738, the second one's about double, 1450. But then when you try to take that 2p electron off, huge jump, 7,770, 730, whatever. So here's a chart showing this. So we see this line between the pink and the purple or whatever color that is. We see this huge jump. First ionization, second ionization, huge jump. 1, 2, 3, huge jump. Okay, and even continues for the nonmetals. So sulfur has how many valence electrons? 6. So I can take off 1, 2, 3, 4, 5, 6 valence electrons, and then whoosh, big jump. Questions?